Alrighty. Um, Welcome everyone. Hope everyone had a good weekend and either enjoyed the snow or has plans to enjoy the snow. Um, let's get going. So last class, or more precisely last week, over the last week, we spent a bunch of time talking about relational algebra as kind of a framework that would allow us to um, reason about queries and kind of reorganize them a little bit. Today, we're going to take the next step and translate relational algebra into practice. In particular, we're going to be talking about today is checkpoint one. And we're going to go over the details of Spark that you need to know in order to implement checkpoint one up, and then also kind of tie that back to some of the concepts that we learned last week. Okay, so before I get to that, just a quick reminder, if you have not already gotten your 5 free points for checkpoint 0, this is your last chance for that. Also, tomorrow night I'll be posting homework 1, and that'll be due a week later. Okay, so let's talk about checkpoint 1. So to start, just to give you a sense of what to expect in terms of how the grader is going to interact with your code. Kind of imagine the grader sitting at a command line and then typing stuff. So obviously the first thing it's going to do is, just like checkpoint 0, it's going to take all of your Scala files, it's going to compile them, bam. Now, in the same directory as your compiled jar file, we're going to find or more precisely, we're going to find a directory called data, and in that data directory, there's going to be a bunch of files. If we want to look at those files, what we're going to see in each of them is something that looks a lot like a CSV file, except instead of a CSV, instead of a comma separated value file, it's going to be delimited by the pipe character. On the US keyboard, it is the same character that is on the top of the backslash. Um, so with this data directory there, the grader is going to run your code. And immediately after your code is run, you should print out a prompt. In other words, a dollar and a greater than sign and a new line. And that basically tells the grading script that you are ready to go. This has to happen within 2 seconds of starting your code. And the reason for that is that later on in the semester, you're going to get a little bit of time to prepare. So this is basically just your code's way of acknowledging that you're good to go. Once it sees a prompt character within 2 seconds, it's going to start issuing a series of SQL commands. Typically one per line, or always one per line. And these are going to be create table statements, select statements, and that's pretty much it. Whenever you see a create table statement, I'm going to emphasize this point and I'm going to re-emphasize it throughout the lecture. Think of the create table statement as an external table definition. So unlike an internal table definition where you create the table and then you have to start inserting or bulk loading data into that table, an external table is one that points to data that already exists. All the table is doing is saying there will be a data file located here, and oh, by the way, here's what its schema looks like, and here's how to read it. Spark has syntax for defining external tables, and we'll be using that. So it'll be create table, then the table name, and then in parentheses the schema, just like a regular create table statement. And then there will be also this using CSV options, a path with a path to the data file, and then a delimiter. It'll always be a CSV file. It'll always be delimited by a pipe character. The path, however, is going to be useful to know. The once you get a one or more create table statements, then we'll also start, the grader will also start sending select queries to your engine. And your responsibility at this point is to parse the query, interpret it, run it, and then start producing output in exactly the same format that you had before. In other words, you're responsible for essentially producing a pipe-separated fields and records, one record per line, and then after that operation is done, after you've printed out all of the responses, print out another prompt. So once again, to recap, when your code starts up, you print out a prompt, and then after you finish processing every command, you also print out a prompt to let the grader know that you are done. To recap, your code will be compiled just the same as checkpoint 0. Print a prompt at the start and after every command. There will be one command per line, so Java's read lines or Scala sources line iterator will give you a full command when you read it. The create table statements will always be external table definitions. They will always point to a file and they will give you the schema for that file. And those files will always be in pipe separated files with very precise location. As you get queries, print out all of the results of that query in a pipe separated format, and then print out the prompt when you are done. If there are any questions, I'll give you a moment to type. Okay, now that may seem like a lot of work. We'll get into why it actually turns out to be a lot simpler than you might think. ideally, we'll by the end of this lecture, we'll have demystified a lot of kind of Spark's internals here. Okay, now the greater, while you are certainly able to bring in whatever libraries you want into your development environment, the grader will only be using one library. One library and its transitive dependencies. Um, a library that contains this simplified version of Spark Catalyst. We're calling it Catalyzer. Um, if you're using a build system based on SBT, which most Scala IDs are, the following two lines. Test. Okay. All right. Sorry for that. Some minor technical difficulties here. All right. We are going to do a. All right. Let's see if this fixes anything. Okay. So, moving right along. So the great. Yes, I'm. My camera seems to be misbehaving a little bit, so we're just going to do audio for the moment, and I'll hopefully get this issue resolved by next class. Okay, so where were we? Okay, so if you're using an SBT-based development environment, then the following two lines of code should be enough to get your compiler working. If if not, then you're just going to have to add a couple of one Maven dependency and one additional resolver to your system. Okay, so from here, the uh, there's a Scala doc for this code available here. By the way, all of these links are on the checkpoint one description. So there's Scala docs for all of this fragment of Spark that you're going to be using. And you're also more than welcome to browse the source code of this fragment of Spark to understand what's going on under the hood. There are links to both of those here in the slides, and there's links to both of them in the checkpoint one doc. Okay, so getting back to the project itself, to recap, what's going to happen is your code is going to be given SQL commands, both DDL, DML commands, as well as queries. So, for example, you might get a create table statement of players, or then a select query on those players. Now, you are more than welcome to write your own SQL parser for this purpose, but Catalyst has its own parser, and you will probably find it a lot simpler to use that parser. Using it is really, really simple. You define a parser object, and then you use that parser object. You call parse plan on it. You give it a string, and out comes a logical plan. Really straightforward. These two lines will basically just do all of the parsing for you, and you don't have to worry about anything past that point or anything up to that point. So what you get is a logical plan, and then that logical plan will encode either a create table statement or a query. You can figure out which it is by using Spark Spark's match, Scala's match command. So this will either be a create table statement, as I said, or a query. If it's a create table statement, then you should register that that table was created, store away all of the information about that table that you need, and that will probably be some combination of the table name, which is a field of the create table statement, the table schema, also a field, and the location of the corresponding data file, also a field of the create table statement. If it's a query, well, then you treat it like, or if it's something else, then you treat it like a query. So let's go into a little more depth on each of these. If it's a create table statement, then essentially what you need to do is you need to take away a couple of things from that from that command. So first off, the command is basically saying there's a table called players, or this particular example is saying that there is a table called players. That table has 7 attributes with the corresponding names and data types, and great. And it's also telling you, by the way, this is stored in a file called data/players.data. Once you have that information, like I said, basically what you will probably need to do is store it away somewhere in a lookup map or dictionary or something like that. And of course, also register the fact that there is a file on disk that contains all of the data that you're going to need to answer queries based on this table. The data, as I said, is essentially CSV formatted, 1 record per new line delimited line, and every field in the record is delimited by a pipe character. Dates in particular are going to be given in SQL standard notation, that is 4 characters of year, a dash, 2 characters of date, of month, excuse me, and then a dash, and then 2 characters of day. So from here, once once a couple of tables have been defined, the next thing that you're going to get is some queries. There's a wide variety of queries that you can get. For the purposes of this particular checkpoint, we're going to focus on relatively straightforward queries. And if you look at the checkpoint 1 documentation, it provides you with a specific subset of the logical plan operators that you need to be able to support. More on that a little bit later. Okay, so how do you get from query to result? Well, there's a fair bit of stuff that happens in Spark from one end to the other. And one thing that we're going to talk about today is well, what does that look like? So in Spark, you can think of this is a little bit of an oversimplification, but you can think of it as basically being 5 steps. So the first step is analysis, where it's going to kind of just do a little bit of sanity checking and cleaning up after the select statement. Um, the it'll do just a little bit of cleaning. I'll get into what I mean by that in just a moment. Let me quickly take a couple of questions. Adesh asks, will primary key foreign key constraints also be there? For checkpoint 1, there will not. We will introduce those in checkpoint 4. Amneet asks, the attributes of tables in the data file in the select query would be in the same order. Yes, so if there is a select star, you should output columns in the same order that they appear in the table. So I'll mention right now that the grader will be comparing your results against SQLite 3. If you ever have a question about how how the grader is going to interpret a particular bit of SQL, see what SQLite 3 does, and like SQLite 3 is really easy to install, really easy to get up and running. It probably already exists on your device. Um, so all you need to do is install it, load the data into SQLite, and then run the exact same query and see what happens. And that's essentially what the grader is going to be comparing you against. Oh, whoops. Okay, if there are any other questions, shoot. In the meantime, I'll continue talking about Spark's workflow. So like I said, Spark starts off by doing a little bit of cleanup on the logical plan. The parser doesn't um, doesn't build a fully operational plan until doesn't build a fully operational plan just because it doesn't have enough information available. So the first step is essentially to replace a bunch of placeholders and do a bit of cleanup on the things that the parser couldn't fully flesh out. Um, then once it has an analyzed plan, it's going to optimize that plan. It's going to rearrange the plan and produce one that is structured a little in a slightly more organized way that produces that we can execute a little more efficiently. Um, After that, also, maybe you can think of this as part of optimization, but what it's going to do then is try and figure out what the best algorithms are for each and every one of these parts of the logical plan. This is known as physical planning, and the output is what Spark calls a physical plan. Once it has a physical plan, then it's actually going to go through the process of taking that plan and converting it into Java bytecode, and that Java bytecode then gets sent out to all of the worker nodes in the cluster and run. Um, Before I get to the next thing, Deepak asks, will we use B plus trees in any way in this project? Yes. So checkpoint 4 is where we'll be doing pre-computation and indexing. So once we get to that point, well before then, we'll have talked about um, logical optimization and incorporating those into plans. Okay, so for checkpoint 1, we're going to take a very simplified view of Spark, of this approach that Spark takes. In particular, we're going to drop the physical planning stage. In some sense, that's going to kind of get incorporated into the code generation step. Um, in other senses, we're kind of going to leave that to the side. Um, Largely as a simplification, our search space for algorithms is going to be a lot smaller than what Spark considers, so we can get away without that additional complexity of also having a physical plan. The other part of this is optimization. So for checkpoint 1, it will be perfectly possible to get an A without doing any optimization on the logical plan. Optimization on your code maybe, but not necessarily optimization on the logical plan. You're certainly welcome to add that, but we're going to talk about that when we get to checkpoint 2. Okay, any other questions? Give a shout, I'll answer them as they show up. Okay, so to put the slightly simplified to give you kind of a more visual way of looking at the approach that I'm going to suggest that you take. We're going to start with the select query. You're going to use Spark's parser to generate a logical plan. Once you have this logical plan, you're also going to have to go through this analysis phase because the logical plan that the parser creates isn't fully fleshed out. I'll get to what I mean by that in a little bit. From the analyzed plan, normally this is where the optimization step would happen, but for checkpoint 1, we're just going to go directly to what essentially amounts to code generation. And what I'm going to encourage you to do is to build iterators for over the results of the query. And then once you have an iterator over the result, then it's just a matter of going over those results and printing them all out. Okay, so any questions so far? I'll give you a moment to type. Okay, so I keep going on about analysis. Well, what does that mean? What does Spark do during this phase? Well, there's basically two parts to it. So the first part, and the biggest part, the part that you'll actually have to implement in this project, is essentially the parser doesn't fully have doesn't generate a fully operational logical plan. It puts in a lot of placeholders, and essentially the uh, goal of this phase is to replace those placeholder values and kind of wire up the attributes that show up in different operators. So for example, a filter condition needs to read from the output of the operator below it, and it needs to know kind of how the attributes line up. I'll get into what I mean by that in a couple of slides. So once we've replaced all of these placeholders, then there's a question of, well, is the query sane? Does it make sense? And so Spark has a couple of built-in tools that you'll essentially be able to just reuse to make sure that all of the types, all of the data types line up. For example, you're not adding one to a date or one to a string. Okay, so I'll get to what I mean by each of these. Let's start with placeholders. So what do I mean by placeholders? So there's a bunch of classes called unresolved something. For example, unresolved relation. Now, the SQL parser does not really want to understand how the system's catalog works. In other words, it doesn't really need to understand how, or we want to avoid the complexity of building the parser with a deep understanding of how tables are stored and organized in the underlying system. The SQL parser's job is simple. It is to translate SQL expressions into relational algebra trees. So whenever it encounters a name, a table, a variable, a function, um, instead of trying to figure out what the meaning of that variable is, it's just going to kind of leave a little bit of a placeholder for that variable. For example, whenever it encounters a table name, it will simply leave an unresolved relation there. Now, you don't have to take my word for it. There's a very handy method on every single logical plan and also every single expression called tree string. And I encourage you to use that like crazy because it really gives you a lot of information. It's a really simple way of just getting a view of what Spark thinks a query is. It literally just spits out the entire relational algebra tree. So for example, if I write select star from R, what I will get back is quite literally select star, in other words, the project star applied to an unresolved relation where there's that R, the table name right there. To give you a sense of what this looks like in Scala code, so the project takes a sequence of targets. In this case, there's just one target, that's star. And it takes as input another logical plan. And in this case, that logical plan is this unresolved relation. There's a bunch of extra goop in there that you don't really need to care about for the purposes of this project. The interesting thing here is the name elements field, because that's basically the name of the table. Now you might be asking yourself, well, why is that a sequence and not just a string? So Spark needs to be able to support multi-part names. So for example, I might refer to some sort of schema or source and say source.table. That would get translated into a two-element sequence of source and table. And for the purposes of this project, there are a bunch of places where these multi-part names show up. For the most part, you can assume that they will always be one-element sequences. Okay, so how do you replace these? Now, the pattern I gave you, or if you see select star from R, well, that's a project sitting on top of an unresolved relation. So what you could hypothetically do is take that project and unwrap it, and then see that below there's an unresolved relation, and just kind of spit out a new version of that. And you could do that, but it's going to be very redundant, involve a lot of redundant code, and just ends up creating a mess of corner cases. I guess what I'm trying to say here is that you shouldn't assume a particular structure on the logical plan. You shouldn't assume that there's always going to be an project sitting on top of a filter sitting on top of blah, blah, blah. Instead, you want to kind of isolate the individual parts of the plan. So Spark gives you a very convenient way of doing this. Essentially, what you want to do here is just anywhere in the plan that there's an unresolved relation node in the tree, you want to just replace that with something else. And Spark gives you a very convenient way of doing that through the transform function on logical plan. Transform as well as transform up and transform down. So for example, if I want to replace unresolved relation with um, with something else, then I can just write plan.transform and then case unresolved relation. That's my pattern. And then on the right-hand side of the arrow, I write a replacement or whatever I want to replace it with. By the way, further continuing Scala tutorial, 3 question marks in a row is actually valid Scala code. It's essentially a way of telling the compiler, I haven't implemented this yet, just pretend that there's something here. If you ever get to that line of code, it essentially will crash. But it's a good way of using the compiler. Like if you're trying to get the compiler to work before you fully implemented a piece of code, if you want to use the type checker, then it's kind of a good habit to get into to leave these placeholders there so that the compiler kind of does its thing. Okay, so that aside, we do need to put something there, right? So what do you replace an unresolved relation with? Now, Spark already comes with a bunch of logical plan nodes that can encode tables. But most of those tend to be fairly complicated just because they have to deal with a lot of other things. So for example, they have to, typically Spark is expecting to read from HDFS or S3 or some other similar data source. So there's a lot of extra goop that goes into authentication, cluster location, a lot of other little details that need to be stored in there, which for the purposes of this project, we don't need. So what I'm going to encourage you to do is to create your own class. This is one of the beauties of the design of Spark. Both of its abstract syntax trees, the expression as well as the logical plan syntax trees, are very easily extensible. You can always create new node types, and as long as you kind of define all of the methods that need to be defined as part of the interface, the appropriate interface, or as Scala calls it, trait, um, then Spark is going to be happy and it will play nice with your code. So for example, if you want to define a logical plan node that represents an actual tree, a resolved tree, all you really need, sorry, a resolved table, All you need to do is extend logical plan, or there's kind of a convenience class called leaf node, which just has no children. It's just saying that it's a node in the tree that has no children. Um, and then all you have to do if you extend leaf node is define what attributes appear in the table. So there's this attribute sequence class, which is just a subclass of sequence of attributes that gives you a couple of extra little details. Any questions so far? And while people are answering those, aha, there we go. Let's try. Hey, that works again. Okay, so where are we? All right. So all you need to do is, in order to play nice with the logical plan, the rest of the logical plan tree, is to just tell the system, well, what are the attributes that show up? Okay. Um, so hopefully this is giving you a sense of how to. So the only thing that you need to be aware of in the logical plan during the analysis phase is these unresolved relations. Um, the parser will also leave a couple of unresolved items for you in the expression subtree as well. And in particular, there's two, for the purposes of this project, or this checkpoint, there are two that you need to be aware of: unresolved star and unresolved attribute. Um, Unresolved star shows up whenever you do select star from blah. Unresolved attribute shows up just whenever you use an attribute name somewhere in in a select or a where clause or pretty much anywhere else. So in both of those cases, what you essentially need to do is replace the unresolved star or the unresolved attribute with one or more actual attribute references. And for this, there's a couple of different variants of this in Spark. The one I'm going to suggest that you use is called attribute reference. So there's a class called attribute reference. It's under the expressions in the expressions package. And what you need to do there essentially is, or like what it takes is a name and a data type. So the attribute needs to know what the name of the attribute is, and it needs to know what the corresponding type of that attribute is. And once it has that, well, then it's happy. But you might note that there's also a couple of other fields here. So there's this expr ID thing here, and then there's this qualifier business. So what are those? Um, well, expr ID, well, first off, how do you pass those extra parameters? This is a little bit of a weird Scala-ism. Personally don't like it all that much, but anytime you call a function, you can actually have multiple parameter blocks in Scala. So if you see this sort of parentheses, close parentheses, open parentheses, is basically just a way of saying, well, I'm going to have a function, but I'm going to kind of organize the parameters into different subblocks. So in this case, essentially, I've got one parameter block for name, data type, nullable, and metadata, and then another parameter block for expr ID and qualifier. But what does it mean? What does this expr ID mean? So this has been mostly a write-only lecture. Now let me get something from you. Here's a bit of code. So I'm defining an attribute reference. the attribute is named A, it is an integer, and then I'm defining another attribute. Its name is A, and it is an integer. If I test these two for equality, what will happen? I mean, there's pretty much two outcomes here. So does anyone want to make an educated guess about which outcome you're going to get? It's pretty much a 50-50 chance. If I bored you all to death, I'm sorry. Yes, they are equal. Okay, that's a good guess. Um, and you'd think that. So the weird thing here is that there's no value. It would be true, 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 or false, return true. Okay, so SQL has a bunch of design choices made to make it easier for humans to use. So for example, we talked about this a couple of classes ago, where an attribute could, we could refer to an attribute as just A, or we could refer to it as table name.a. Similarly, we could have multiple attributes with exactly the same name in the output of some relational operator. And there's a bunch more weird corner cases that uh, just in the bulk of our code, we don't want to really have to think about. So here, this particular comparison will return false. And the reason for this is important to understand because Spark does not look at the name when deciding whether two attributes are the same. It doesn't look at the type when deciding whether two attributes are the same. Two attribute references are the same if their expression ID is the same. And if you actually print out the attribute reference, you'll see the expression ID as part of the attribute name. So here, because I've created two different attribute references, as you can kind of see here in the code, if I don't provide an expression ID, what it's going to do is allocate a new one. It's going to create a brand new expression ID. And what's essentially happening here is that I'm creating an attribute with one identifier, and then I'm creating a new attribute with a different identifier. And because those identifiers are not the same, I end up with, as far as Spark is concerned, two different attributes. So I mentioned earlier today that one of the responsibilities of the analysis phase was essentially to wire up the attributes. And this is basically what I mean. Essentially, what we want to do is we want to resolve the attributes, but we want to resolve them in a way so that the expression ID of the attribute reference lines up with the corresponding expression ID of the output of the operator that is coming in. Um, so if I create just a brand new expression identifier, and I use that identifier as an input or as when creating both of these references, then everything will work out. Any questions? All right. Give you a moment to type. And all right. Okay, so the other part of that second parameter block, and that, as we're going to talk about, is actually going to be kind of useful here, is the qualifier. Oh, question. Is it possible to have two attributes with the same name in a table, asks Yeshi. Yes, it is possible to have two attributes with the same name in a table. And that is exactly why you need the expression IDs. So internally, once you've gone through analysis, all of the attributes should be wired up. They should have the appropriate expression identifiers. And at that point, you can stop looking at the name and just look at the expression identifiers in order to determine which attribute you're talking about. You can rename the attributes. The names stick around mainly for debugging purposes, but what really identifies the variable is the expression ID. Okay, so the other part, I want to introduce one other bit of background on Scala. So anytime you have optional parameters in a function, that um, you can use argument equals value to pass a specific parameter by name, a specific function argument by name. So for example, I have expr ID and qualifier. I don't want to provide an expr ID, but I do want to provide a qualifier, so I can just write qualifier equals blah, and this is basically the pass by name semantics that you see in Python, many other languages. Okay, that aside, um, ah, Jeshla asks, the expert ID represents the attribute as in the column name or the attribute and its value combined? That's a good question. So so here we're talking about expressions in the abstract sense. So 1 plus A, there is no A. Until we tell you evaluate that expression on a scope where A is equal to 3 or A is equal to 5. So to answer your question, it's the first one. The expr ID represents the attribute, the identity of the attribute. We'll get to evaluating things in, I think, 2 or 3 slides. That'll be when when you actually start getting values for the expression. But an expression tree just represents a computation, not the inputs to that computation, or encodes a computation, not the inputs to that computation. Okay. Right. So qualifier. What is a so the second parameter in that second parameter block of attribute reference is a qualifier. What does that mean? Well, it's just a way of saying of putting all of the qualifiers on that attribute name. So if I write, for example, the attribute bar.foo, in other words, the attribute foo in the table bar, that bar part is going to show up in the qualifier. And just as before, the qualifier is a sequence, and you can generally assume that that sequence is going to have only one element in it. Okay, Jisha asks, right, so the expert ID would represent 1 plus A. Not quite. So the expert ID would appear only in the attribute itself. So that particular formula has one attribute. It has an A. So when we instantiated that, let's say our input was an operator that had let's say X with expr ID 1, Y with expr ID 2, A with expr ID 3. And we had to figure out what, actually, you know what, let's draw this out. So anytime we evaluate an expression, we're always going to evaluate it in some context. So for example here, we have 1 plus A. Now, if A starts out as an unresolved relation, or sorry, unresolved attribute, we have to resolve it in the context of something. So let's say, for example, that what we have what we get from the parser looks like this. I'm not going to encode the entire thing. I'm just going to say 1 plus A. And that is applied to some table. And that table has a schema of X with attribute ID, with expr ID 1, Y with expr ID 2, and A with expr ID 3. So if we're trying to resolve, so essentially what we want to do here is we want to figure out, well, which attribute is A referring to here? So the simplest thing is just to look at the attribute names. So here our schema is X, Y, A. And during the resolution step, essentially what we want to do is kind of take this and recognize that what we're talking about with this attribute is actually this A with expr ID 3. So then as far as we're concerned, for the rest of um, the life cycle of this logical plan or this expression, all we're concerned with is attribute number 3. Or in other words, essentially what we're going to turn this into is the expression 1 plus A with expression ID 3. Hopefully that clarifies things. Right. Okay, so the qualifier. The qualifier, like I said, is just a way of saying that the table that a particular attribute comes from. Now, you don't actually need to use this, but Spark already uses it. So anytime you have a, a subquery, for example, Spark will automatically readjust the qualifiers on the attribute references that get produced out of that particular operator. So you don't really need to use this, but it actually does help if you do. Okay, so I've been talking about analysis for quite a while, largely because this is going to be a major chunk of the project. Um, why do this in the first place? Um, as we start talking about the implementation, the iterator construction and execution, you may be tempted to actually combine the two, to do just one step that does both code generation or both iterator construction as well as analysis. And I'm going to suggest that you don't. I'm going to suggest that you actually do this as two separate steps, pretty much for two reasons with a little bit of a third. So the first is that as you're building iterators, it is often very useful to know the schema of an operator. So if you're building a filter, you kind of want to know where in the output of that filter you can find a particular attribute so that you can evaluate the condition on that input. So you're going to need to know the schema, and Spark already provides you with code that will, for most operators, give you the schema of that operator automatically. There's this output command, and then there's also a schema command, both of which will essentially tell you what the schema of a logical plan node is. But those functions will only work if you resolve the plan. It doesn't know how to interpret the schema of a placeholder. So first and foremost, if you implement analysis, as I'm suggesting, you will get schema construction for free. The second thing is data type. So expression nodes in general can tell you what the output is. For example, if you have 1 plus A, you don't need to do any sort of tree traversal to figure out that that's going to produce an integer. Um, the system will just be able to figure that out automatically, and it exposes that through the data type function. But again, in order to figure out the data type, the expression tree needs to be resolved. So if you do the analysis step first, then when you're actually doing even more of the heavy lifting, especially in later parts of this project, checkpoints 2 through 4, you will have a bunch more capabilities available to you. And of course, as we'll get into in a moment,
Oh,
okay. Technology, I hate it. Okay. Sorry about that. We're gonna try and do this. Okay. Okay. I will be trying to figure out what is going on here. For next lecture. For now, all right. So, where are we? Okay, so hopefully I've convinced you by now that it is a good idea to separate analysis into 2 separate steps. If not, please talk to me afterwards. Okay, so on the so in terms of expressions, in principle, we could have you uh, write all of the logic for evaluating basic arithmetic. But I mean, that's something you'll pick up in 505 or one of our other PL classes. Um, we're going to kind of just give you all of the logic for evaluating expressions. In particular, we're going to give you well, this is actually part of Spark. There is a function on every single expression called eval. And eval takes in an input that is this internal row class. We'll get into that in a moment. And it's going to produce an output, which is going to be one of several different classes, depending on the data type of the corresponding expression. I'll give you a table that defines all of those in just a moment. Eval is implemented already for nearly every single expression node. So given an expression, you should just be able to generate an internal row and call eval on it. However, if you were paying attention, if you enjoy paying attention to little details, there's this annotation, or there's this trait on attribute reference, unevaluable. And well, true to the name, that actually means that attribute reference can't be evaluated. Why is that? Well, the reason is that internal row is basically just a thin wrapper around array, an array of arbitrary objects with some convenient accessors for specific data types. And unfortunately, attribute reference, while it does have a unique identifier for the attribute, it does not actually have any idea where in the input table that particular attribute is going to be, which position in the input the attribute is going to be at. So what I'm going to suggest to you is just like you built a table class that you could plug in into a logical plan, I'm going to suggest you create your own row lookup class that you can just plug in to expression. So reasonable question you might ask here is, well, why use this instead of attribute reference? And I'm going to respond basically by saying that in this checkpoint, it may not be a huge deal, but in later checkpoints, especially once we start optimizing in checkpoint 2, there's a bunch of different optimization rules that will change the schema of an operator somewhere in the tree. And because it can change the schema, it can change the position of a particular attribute. So it kind of makes sense to go through essentially 3 phases. One where kind of the initial phase where you just have unresolved attributes. The second phase where you refer to attributes by their identity, and then the third phase where you actually where you essentially commit to a very specific schema and then pick a particular position for each attribute and then rewrite the expression again so that it has the expression at a particular position. Right. Okay, so this is how you evaluate expressions. In the last couple of minutes, and we'll go into even more detail on this next class when we talk about algorithms, but you can create functions, you can create logic to evaluate arbitrary trees of logical plans. And in some cases, you might actually even be able to get an optimization, get some performance boosts by doing that. But I'm going to suggest, at least initially, that you do this in as simple and as composable a way as possible. So essentially look at each individual logical plan node individually. The logical plan has some input tables. Just assume that we have some way of translating a logical plan into a table. And given the input tables, then just try and figure out how to produce the output for that one specific operator. I'm going to start off presenting this with a naive implementation, naive approach to implementing this that you really should not use because it will get you in trouble in checkpoint 2. But it kind of helps to illustrate this mentality. If you're comfortable with recursive algorithms, feel free to tune out at this point. You're not going to really get anything too new. But like essentially what we're trying to do here is look at each individual node one at a time. And one way to kind of do that is to pull out the logic for each individual node into a separate function or a separate class. So for example here, if I see a project node, in order to produce the output for that plan, then essentially what I need to do is have an input. And to get that input, well, that's pretty easy. What I need to do there is compute the, just recursively apply the same logic to whatever the child is. And then once I have a table representing the input to the operator, then I figure out, well, how do I transform that table into a table in the output? Okay. One other thing I want to bring up here, and that's representing the table. So eval already takes internal row as an input. And so I'm going to encourage you to use internal row as your representation of a row. And well, what is a table? It's a collection of rows. We can treat it as a sequence of rows here if we want to represent the entire table. Now, to kind of step away from the recursive logic here, essentially the mentality we want to approach this with is we kind of want to start from, There we go. We want to start from the leaves, and just for each of those, we want to read them in, build a table for each of them. Then we have an operator, and we essentially want to evaluate the logic behind that operator and then produce a new result. We have another operator, evaluate it, produce a result. Another operator, evaluate it, produce a result. Just one at a time. For every operator, we evaluate it and we produce a result. Now, I said this was naive, and one more thing. So for example, for filter, we get a table as an input, and we have some sort of condition that we want to apply to it. Well, what do? We scan over all of the elements of the table, and we filter out everything that doesn't match the condition. Lucky you, Scala already has this implemented. There is a very convenient filter method that you can apply to every element of a sequence, and then essentially that will filter out all of the items that don't match the particular condition that you're looking for. That being said, and my advancing the slide may have given this away, this might not necessarily be the best idea. In the interest of time, I'm just going to blaze through it because we are, basically because a table, if we try and represent the entire table, we're storing that entire table in memory, and that can take up a lot of space. So instead of doing that, what I'm going to encourage you to do is build your table using iterators. So what do I mean by iterators? Well, if you're not already familiar with the Java interface, or equivalently the Scala trait, an iterator is a class that implements two methods: hasNext, which tells you if there are more elements in the iterator, and next, which actually produces the next element. For the purposes of this class, I'm also going to suggest, or this project, I'm also going to suggest that you have a method that allows you to reset the iterator. And all of these functions that transform tables can be implemented as iterators. And in fact, you can implement them in such a way that they use a constant and relatively low amount of memory. How does this look like? Well, if you implement this in select or a filter, essentially what we're doing is when getNext is called on the filter operator or the filter iterator, it's going to read one record from its input, look at it, see if it evaluates the condition, and if it does, it's going to return that. Great. One round of iteration. The next time getNext is called on filter, it's going to grab the next record out of the iterator, check to see if it applies meets the condition. If it doesn't, well, then we drop it and read the next one. Repeat the process. That one matches the condition, return it, and just keep going. Eventually, you get to the end of the input. The select can no longer read any inputs from its own input iterator, and so it is also done. Now, if you're paying attention here, so Scala is designed for working with collections. And if Scala provides you a bunch of extra stuff on top of iterators. Just by defining the iterator, by extending or implementing the iterator interface, you get a ton of extra bonus features. And those extra bonus features, if you pay very close attention, mean that you don't really have to think a lot about how to translate the logic for your code on a table to equivalent code with an iterator. Okay, so last 5 minutes here. Joins. So we're going to talk about more detailed algorithms for joins next class. For today, I'm just going to say and in particular for this checkpoint, I'm just going to say that the simplest way of implementing this is going to be enough to get an A. Literally loop over all of the elements of one table, and every time for every tuple of one table, called the outer table, we're going to loop over every tuple of the other table. I'm going to call that the inner table. And then we're going to glue the outer tuple onto the inner tuple and produce a result. You'll note that there is no checking for conditions here, and that's because in general, what I'm going to propose, what you need to do in checkpoint one, you will be able to get away with without actually doing any sort of actual join. You'll be able to express the join as a Cartesian product, which you have here, combined with a filter. Combining the two will give you the full join. Adesh asks, will iterating all rows of the entire table be very complex? It'll be a little more complex than operating over the table, but like I said, Scala actually is going to make your life a lot easier here. It provides you a lot of really nice and useful methods for working with iterators. So if you haven't already taken a look at the Scala doc for iterators, I encourage you to check it out because there is a ton of useful stuff that you will be able to reuse when building this project. Right, so this algorithm here is iterative. It operates over the entire table. One of the things probably, this might be a little bit of a challenge, translate this into an equivalent iterator. Okay, your input data is going to, as I said, be given as pipe separated value files. There's a class in Scala called source in the scala.io package. It has a method called line iterator that is going to give you an iterator over each line of the input. From that iterator, you're essentially going to want to look at every row one at a time. That sounds almost like a map operation. Every row or every line of text one at a time, split the fields of the string, and then dump it all into an internal row. There's a handy method called fromSequence that will take an array or a sequence to produce an internal row. Now, just to emphasize this point, I went through an example with you. I went through an example using the entire, where the code looks at the entire table all at once. Please, 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 please do not do that. You will get away with it in checkpoint one, and then you will cry in checkpoint two. Do not operate over entire tables. Please use iterators. Okay, so I told you earlier that I'd give you a mapping between the different data types. So in SQL, if you see a create table statement, the corresponding types will be string, int, float, decimal, and date. Those are the ones we're going to be using in this project. The corresponding Spark type, so this is in the Org Apache Spark SQL types package. There's string type, int type, float type, double type, date type. And then there's the objects that you get back from eval, and that eval in turn expects as inputs, are going to be pretty much the standard things that you'd expect in Scala. The two weird ones here are dates are expressed as java.time.date, and strings are expressed as this custom UTF-8 string class that Spark defines. And there's a handy way of going to and from that, going back and forth between those strings and regular Scala strings. All right, that's it. Sorry I went a minute over, but I'll be around if anyone has additional questions. And next time we'll talk about some slightly more intelligent algorithms than just doing Cartesian products all over the place. Alex asks, I have a question about the checkpoint zero. I accidentally overwrote my .git. Should I redo the entire git procedure, then do the add commit and push? No, so if you accidentally overwrote your .git file, just do essentially you should just be able to start from the checkout step. So redo the git checkout, and you'll get a fresh directory with a fresh .git file. All right. Don't see any other questions lining up, so I'll see everyone on Thursday.